Okay, 413, day one. How can we describe any figure? We're going to use using variables. It should say, I think, use variable to generalize. Now it's time to do some algebra stuff, right? So when we understand patterns and extend your thinking to make claims that apply to any figure, you are using a thought process called generalizing. Generalizing is one of the most important parts of algebraic thinking. In this lesson, you and your team will work together to generalize using the methods you developed in 4.1.2 to describe the number of tiles in a square frame of any size. So your goal is to be able to say, hey, how many tiles are there, no matter if it's 10 by 10, 100 by 100, or whatever, right? So the diagram below uses one method you can represents one method you can use to find the number of tiles in the frame of a 10 by 10 square, using the diagram to answer parts A and B below. Look at your work from yesterday's 4-13. Whose method was this? So let's look at that. 4-13. And what do we have? Okay, so here we are. If you go back to that, what we find is it was Tina's method. Tina's method that was the representation. So let's go back here. In here. So this was Tina's. Tina's method, remember, was the 10 plus 10 plus 8 plus 8. Okay, that was Tina's method. Use that method to determine the number of tiles in a frame of a square that is 18 by 18. Okay, well, we know that on top it's 18. We know on the bottom it's 18. Whoops. Right, but what would each side have to be then? Each side would have to be, looks like 2 less, so 16 and 16. 18 plus 18 plus 16 plus 16. Now I'm going to put, when I go to find out what that would be, I'm going to double my 18s to get to 36, and I'm going to double my 16s to get to 32. I'm going to put those together to get 68. Okay. Can you describe how to use this method, how to use the method described in problem 421 to find the number of tiles in any square frame with any side length? Work with your team to write a general set of directions and words that you describe on how to calculate the number of tiles in the frame of any square if you're given the side length. Well, the top is, right, the top and the bottom are going to be the number, the side length. So we could say side length plus the side length, right? Because that would be the top and the bottom. That's the top, and this is the bottom. All right, so those are side lengths. And then we have to add the two sides, don't we? We got to add those two sides. I'm going to move that over. So we could say this is like the left, and then we could say this is the right. And we'll put the plus signs in between. Actually, we could just do this, right? And what do we know about the left side? Well, the left side is not the side length, but it is the side length. But we have to subtract the top and the bottom. So we could say minus 2. And the right side is going to do the same thing, isn't it? We're going to do the whole side length, but we have to subtract 2, the top and bottom piece, right? If you think about it, right? This whole thing was 18 before, but we had to take away the 1 and the 1. So it was really the side length take away 2, wasn't it? Side length take away 2. So here we go. What if you wanted to send the directions from problem 4-22 in a text message? When people send text messages, they often find ways to shorten words. For example, they might use a letter that sounds like a word such as you instead of you. They might also use an abbreviation like BTW instead of by the way. In 411, you used a variable such as x to represent an unknown number for the distance Croaky traveled in one leap. In that case, your variable represented a number that you did not know in a specific situation. Now, you're going to use a variable in a different way to represent a number that can vary within a given situation. You have written a set of directions for calculating the number of tiles in any square frame. How can you use numbers and symbols to shorten your directions? With your team, find a way to shorten your set of directions by using a variable such as x to stand for the number of tiles on one side of the frame. Okay, well, if we have to use x, right? If we have to use x to represent the number of tiles on one side of the frame, if I could think about it, right? I'm looking up here. That means that my side length, right, has to be what? It has to be the x. So that's Let's do that. So that's if the x is the, just to think about it, like it could be the top, right? Meaning that it's the side length. Then what did I do? I added the bottom. That was also the side length. So I'm going to have to add another x just for the bottom, right? Then I have to add the left side. The left side was the side length, but we had to take away 2. So we could say that's the side length is the left side. I'm sorry. The left is the side length, take away 2. So it's the x minus 2. I could put parentheses around there because I should subtract 2 to get that number, shouldn't I? Right? Plus the right side, and the right side is the side length, take away 2. X minus 2. So those parentheses say, hey, we're going to group those together. I think we've talked enough about parentheses yet, at least. So, and actually in this case, if you didn't put the parentheses in, it actually works out just fine. You don't have to put them in there. So you can see, hopefully, the different parts, right? I can see my top. I can see the bottom. I can see the left. And I can see the right. Okay. All right. All right, now we need to choose a different method from 412 for counting the number of tiles in a square frame. Work with your team to shorten this method into an algebraic expression, combination of numbers, variables, and operating symbols like addition, subtraction, multiplication, all that stuff. Be prepared to share your idea with the class. Okay, so let's look at 4. Let's go back. Let's choose another method. What would be a nice method for us to do? So we already did Tina's. Let's choose a different one. Let's choose one with multiplication. Okay, let's do TJ's method here, right? We did 4 times 8 plus 4. Let's review that method. Okay, so TJ decided to do, the side length on here was 10, but in order to get the 8, we had to do a subtract by 2, didn't we? We had to subtract by 2. And then we did 4 of those because there were 4 sides, but then we had to add the 4 corners back, right? So we didn't forget about those. Let's do TJ's method. 4 times 8 plus 4, but we got to change that with variables, don't we? Well, you know what? Let's do it here, and then let's carry it back over. All right. So the 4 side, this 4, right, represents the 4 different side lengths. Well, we still have 4 different side lengths, but the 8 is a tricky part, right? The side length for any piece, in this one it was 10 minus 2, but the side length we used is a representation of x, and we had to subtract 2. So we took that side length and we subtracted 2. Now there's one little problem right now, right? The thing is we must take and subtract the 2 each time first. So we have to use parentheses or these grouping symbols because that has to be the side length. We have to take the side length, take away 2, and then we multiply it by 4 for the 4 sides. And let's not forget about the 4 corners, right? Let's not forget about those 4 corners. That's a tricky problem. I mean, if you could see that, that's pretty difficult. I'm going to cut that, and I'm going to put that over here in 413. We did all our hard work. Oops. Oh, please paste. I've had problems with it not pasting in very well. So we had to take each side length, and we had to subtract it by 2, and then we multiply it by 4 for each of the 4 sides. Then we had to add the 4 to it. I don't remember whose name that was right now. So compare the 2 expressions that you created in problem 4-23 and 24. The expressions both represent a number of tiles in a square frame of any side length, so they are called equivalent expressions. For example, there are 36 tiles in a 10 by 10 frame, no matter how you count them. For both expressions to work, you should get the right number of tiles for any particular frame. How can we check those 2 expressions that are equivalent to see if that they're equivalent? Well, we could. What could we do? We could just try an example, right? Couldn't we just use our own example? example of any length, couldn't we? Any length. We could put in there, like 10 and, well, we already did 10. So we could do like 5, couldn't we? We could do it as 5. So if I use Tina's method, x plus x minus 2 plus x minus 2, let's try that. Her Tina's was x plus x minus 2 plus x minus 2. And what if we wanted 5 in there? We would say 5 plus 5 minus 2. Whoops, got a little lazy there. 5 minus 2, which is 3, plus 5 minus 2, which is 3. 5 plus 5 plus 3 plus 3. 5 plus 5 is 10. 10 plus 3 is 13. 13 plus 3 is 16. Now let's try it with the other method right up here that we just had from there. So 4, parentheses, x minus 2 plus 4. 4, parentheses, x minus 2 plus 4. Let's try 5 in there. So 4 times 5 minus 2 plus 4. 5 minus 2 is 3, so 4 times 3 plus 4. That's 12 plus 4, which is 16. Did I have that same one? I did, right? So 16 and 16. That kind of shows that those two expressions are equal. All right. Jared is playing around and creating the following expression for fun. Are they equivalent? How can you tell? All right, so how could we tell? We could just do, we could plug in a number, right? We could just try something that might work. Let's choose 3. All right. Now, when you see it like this, this means 2 times x. So 2 times 3 plus 2. 2 times 3 is 6. 6 plus 2 is 8. Let's try it over here. We have to use the same one, right, where we're saying x equals 3. So let's try this. 3 plus 1 plus 3 plus 1. 3 plus 1 is 4. 4 plus 3 plus 1. 7 plus 1 is 8. And let's do it over here. 2 times 3 plus 1. 2 times 4. We could keep the parentheses around, but we don't need them anymore. 8. Well, let's check. 8, 8, and 8. Hey, are they equivalent? Yes. How did we tell? They were all equal to the same number when we put in the 3. Now we could do the same thing down below. Are these two equivalent, right? Are these two equivalent? Let's plug in some numbers and let's see. What do we want to try for x in this time? Let's try 4. X must equal 4. We're going to check it. 5 plus 4 times 4 times 4. Ooh, I feel like I should have picked a smaller number. Then we have 3 times 4 plus 5. All right, let's see. 5 plus, now we have to multiply. 4 times 4 is 16. 5 plus 16 times 4 is 64. 5 plus 64 is 69. Let's check this one. 3 times 4 is 12. 12 plus 5 is 17. Are they the same? No, they're not. We have two different numbers, don't we? All right, there we go. If you have any other questions, please let me know.